Let's say that Kelton and Aoife happen to live next door to each other. I don't know if you guys do or not, but let's say that you live next door to each other. Same neighborhood, same size driveway, pretty much same size house, but identical driveways. It's the end of May, and we get this freak snowstorm. It blankets 80 centimeters of snow on both driveways. Aoife and Kelton get up in the morning, both of them get up in the morning, and they get excited because there's so much snow. And Mom says, hey, good news. School's canceled. And then they're thrilled, and they're like, I'm going to go back to bed. And then Mom says, wait a second, don't go back to bed. You got to shovel the driveway. So Kelton goes out there to shovel the driveway. Aoife goes out there to shovel the driveway at the same time. They say, hey, how's it going? School's canceled. Did you hear? Yeah, I got to shovel the driveway. Oh, me too. So they start shoveling the driveway at exactly the same time. Aoife takes an hour and a half to shovel the driveway because there's a lot of snow in that driveway, 80 centimeters of snow in that driveway. Kelton takes 4 hours to shovel that driveway. He's a little slower. Here's the question. Who did more work, Aoife or Kelton? Same size driveway, same amount of snow, but Aoife did it almost 3 times faster than Kelton. They both did the same amount of work. Okay, if I'm hiring somebody based on how much work they can do, I'm an employer and I'm hiring somebody based on how much work they can do, I don't care who I hire there, right? Because they both do the exact same amount of work. In the end, they both expended the same amount of energy in shoveling that snow. Identical amount of snow, they had to both put it on the side of the driveway. Okay, they both used the same amount of energy, therefore they both did the same amount of work. But if I'm an employer and I'm hiring and paying by the hour as opposed to paying by how much work they did, then I do care how quickly they work. We need to quantify not only how much energy was expended in the work, which was exactly the same in both of those cases, but we need to quantify how quickly they do that work as well. The way that we quantify how quickly they do that work is by a concept called power. Power is not work, but it's closely related to work. It's the rate at which work is done. Just like acceleration is not velocity, it's the rate of change of velocity. And velocity is not displacement, it's the rate of change of position. Power is the rate at which work is done. So work is the same for both of them in that situation. The power isn't. Who is more powerful in that case? Aoife was more powerful, right? Because she did the same amount of work, but did it quicker. The equation that we're going to use to describe power, by the way, is the symbol for it is capital P. Anything that's a rate has time on the bottom. And that should make sense, right? Aoife did it quicker. Her time was smaller. If her time is smaller, then her power is bigger. So time has to be a denominator. Power is equal to work over time. What do you think the units are? Take a look at the equation. What do you think the units for power are? Joules per second. Now we got work over time, which is joules per second. Now, what do you think another set of units for power is? Same thing as a joule per second. What is another set of units for power? Listen carefully. Listen carefully to what I'm saying. What is another set of unit for power? No. What is another set of unit for power? No. What is another set of unit for power? Watts. Somebody got it finally? I told you. I just told you. Watt is another set of unit for power. It's a watt. Now, is power a vector or a scalar? It's a scalar, right? When you divide a scalar by a scalar, you get a scalar. And of course, you know it's a scalar because there's no little vector sign over top of it. Let's do one quick example, and then we'll wrap it up for the day here. The question says, example number 14 says, a 60-kilogram person runs up a set of stairs, which is a vertical distance of 10 meters and a total time of 4.5 seconds. What's the power output of this person? We're going to say power is equal to work over time. We know the time here, it's 4.5 seconds, but we don't know the work, so we've got to find that. Work is equal to F times D, but work is also equal to delta E, which is EF minus EI. Now, what kind of energy does this person have at the top of the stairs? Potential energy, because there's that height, right? A height of 10 meters. So we're going to say the final energy here is gravitational potential, mgh. Now, what kind of energy does this person have as they're standing there ready to go up these stairs? Nothing. The initial energy is 0. So my change in energy or my work done is just mgh. We're going to say it's 60 times 9.81 times the final height of 10 meters. That's going to give me 5,886 joules. So let's sub that number in here now, 5,886 joules, divided by 4.5 seconds. That gives us a power output of 1,308. We could say joules per second, or we could say watts. That's going to be 1.3 times 10 to the 3 watts. That's a lot of power, actually. That's pretty high. That's almost 2 horsepower. We define a horsepower as 750 watts. Okay, this person has almost 2 horsepower. Now, granted, that's over a very short period of time. It's unlikely that a person could maintain 2 horsepower for any more than, 5-6 seconds. Here's your homework for tonight. Oh, you thought you got away with none. Your homework for tonight is, you probably knew what it was already because it's on the board, worksheet number 19, which I got to give you here, questions 1 to 3. There's 6 questions on the worksheet. I only expect you to do the first 3 tonight.